Welcome to Lab 2. Here we're going to study and predict the motion of a falling object. The physics we're using in this lab is Newton's second law, which looks like this. With some algebra, we get this form from the original law, which we're going to use in this lab. To start, I have this video of a light bulb falling to the ground. First, I need to set the length scale. Then, I need to set the coordinate system. I choose the origin to be the initial position of the ball, the positive y-axis pointing up and the positive x-axis pointing to the right. Here the ball is falling from rest, so the initial velocity is equal to 0. And I track the motion of the ball to get this position versus time graph, which I'm gonna use later. Now I open Python to make the computer model. Here I set the mass of the ball to 30 grams. And the initial position is 0 according to my choice of the coordinate system. The initial velocity is also 0 as the ball was dropped from rest. T is equal to 0, and this is where we choose to start our clock. Delta T should be small enough compared to 1 second, which is the whole period of motion. G stands for gravity. J hat, which tells the computer where the positive y-axis points. B, the drag coefficient. I'm gonna use this one later. Now let's take a moment to see what forces should we include in our model. First, let's assume it's only one force, the weight force. W equals negative mg j hat. Okay, let's apply this. Let's set F net equals W, only the weight force. Let's just ignore this line here and run this. This arrow here represents the weight force, and this is the position versus time graph. If we compare the two graphs we got earlier in one chart, where the horizontal axis is the time in seconds and the vertical axis is the position in meters, we get this. In earlier times, we see that the graphs are close to each other, but as time increases, the graphs are not close anymore. So there must be another force acting on the ball, drag, which is equal to negative bv squared, where b is a drag coefficient that we mentioned earlier. Now let's apply that to Python and see what we got. This time, we can see another force added, and it's proportional to the speed of the ball. And that's why its magnitude is increasing, not constant like weight. We can put this new graph with its mates, and here's what we got. The new graph is gray. It's too close to the experiment graph, not the same, but too close. And the reason why they're not the same, maybe because there's a third force that's acting on the ball, but I'm not gonna mention that here. Now I have two important questions that I should address in this report. The first question, what does it mean? And I think we've discussed this part earlier here. Second question, what if the object was thrown down instead of dropped from rest? Okay, let's see what happens when we change the initial velocity. I'm also gonna change the print order here to print the velocity of the ball instead of the position, so I can compare the results. Okay, we can see that the graph became more flat here, so the graph has totally changed and the final velocity has also changed. Why did all that happen? Well, if we look here again, we find that the drag force is proportional to the square of the velocity. So if we change the initial velocity, the drag also changes. And if the drag changes, F sub net also changes. So if we look again to Newton's second law, we find that we've changed F sub net and we've changed the initial velocity, so the final velocity must also change. This is it, and thank you for watching.